Hello, physics students. Buckle down, because we're about to go for a pretty deep dive into conservative forces and potential energy functions associated with them. Woo! Sounds like a barn burner, huh? It's pretty cool in the end, and leads to some fundamental truths about, about conservative forces and potential energy functions. Who cares? I don't know. I guess it does. Well, like I said, at the end of this presentation, you do get to something pretty neat, pretty maybe unexpected but cool about fundamental universal behavior. So let's please consider an Earth particle system. And a particle is moved from, well, this location that we've called start to this location we call end, and I don't know, it takes some path to get there, like this. Sure, fine. Well, parts of the system, and that means, well, the particle and the Earth, sure, each of those particles, a particle can have kinetic energy only, right? A particle can move and thus can have energy. A particle can only have kinetic energy. A particle is assumed to be completely simple in its nature, like it doesn't have any internal structure and thus isn't made of things that can be moving. So we can't account even for internal energy, can't account for temperature of a single particle. So a single particle, when we really simplify this thing can only have kinetic energy. But the Earth particle system can have, by definition, what we call gravitational potential energy, because, for example, Earth makes a gravitational field, the particle's in that field, and vice versa. The particle makes a gravitational field. It's pretty weak, but it's there. Earth is in that field. And so that two-particle system has what we call gravitational potential energy. And this system's, well, let's call it UG, because we call this UG. That system's gravitational potential energy can be changed by the act of doing work. And let's say maybe on the particle. A lot easier to do work on the particle than it is on the Earth. Okay, so, yeah. And, well, the deal is, if we're going to move this object from here to here in the y direction, well, the amount of work that we would say, I don't know, F times, well, delta x, quote, and by times I mean dot product of, and by delta x I mean change in position. So how about delta r? I like that better. Well, the minimum amount of work you'd have to do to move this thing from one place to another is, well, the minimum force you could apply to move something upward is mg. Right? If you apply more than mg, you could accelerate the object upward, but you don't have to. I mean, to get it moving, you could apply more than mg, but then to stop it, you could apply less than mg. But on average, the minimum amount of force you have to apply to move something upward is mg. And this delta r, really, well, the minimum distance would be a delta y. And that's, we could even say like mg delta h. And we recognize that as the change in potential energy of the system. Right? So in this case, the minimum work we do is delta UG. And we do, I'm saying something other than Earth particle is moving particle. All right, so that's the work done by, third party. Let's consider the work done by mg as we move an object from start to end. And let's consider three different arbitrary paths. Let's take one that looks like this. We literally move the thing like up and then over. There's path one. And then path two, how about we take it the straight route here. There's path two. Path three, let's just go nuts and take it around the bend and, oh boy. Sure, there we are. There's path three. Do your best to sketch that as exactly as you can. So let's just take, how about path one? And let's talk about the work done by mg. All right, the work done by mg. Well, that's going to be equal to, well, we could simplify to a statement like F dot delta x, but what I'm going to do is let's be explicit and say, by definition, the work done is the integral of the F dot, and I'm going to use our text notation, dl. Right, we have to add up every little bit of work, because every one of these, right, what we're saying is there's a little tiny amount of work done that's equal to the force applied over some tiny little distance traveled, as long as there's some component of F that's parallel to the direction of motion for that little tiny displacement. Mr. Torres, you following all this? Wake up. That's a joke for my sub. Okay, we're fine here. Let's say this is mg, and let's assume here that we are near Earth's surface. Okay, so we're going to say that, well, we can define this mg force. And mg as a vector, well, is mg, has magnitude mg. This gravitational force has magnitude mg, and it points downward in the negative j hat direction. So I'm using a I hat, j hat coordinate system. Okay, dot dl. Dot dl. Well, note that mg is a constant, right? If we're in this room / near Earth's surface, then work done by mg, we can pull out this negative mg in the j hat, and we can integrate dl. All right, that's like integrating dx in the I hat and dy in the j hat. It's really like integrating both of those. And so this work done by mg is negative mg in the j hat. Well, if we integrate these things, and we're saying really like from position 0 to position final. So what we're going to get is times, well, really a delta r in the I hat plus a delta r in the j hat. What I'm saying is this integral is really delta x, but from here to here, so that's delta r. And this integral, we're really integrating both of these. This is delta y, or it's just really y evaluated from r0 to r. So that's a delta r. So it's probably more appropriate to call these work as negative mg j hat. It is more appropriate to call these a delta x in the I hat and a delta y in the j hat. And so what I didn't put in here is we're really dot producting these things. We have to keep that dot product. So we're dot producting now scalar product of mg in the j hat and that vector. All right, well, the j hat dot I hat stuff is 0, and we get that the work done by mg is negative mg. Well, look, this j hat dot j hat is 1. And so we keep the delta y, and we get a delta y, and there's our answer. And maybe we recognize this as, oh wait, that's the negative delta ug. The work done by mg is negative delta ug. Which path? Oh wait, was that for path 1 or path 2 or path? Shoot, which one? Oh wait, every single one of these paths, this is true for, right? This is the force for every path, or it's mg regardless of path taken, that's for sure. It's the gravitational force regardless of path taken. This, the integral dl, is that for every path taken. You know, there can be there have to be some, you know, change in x position. There have to be some change in y position. The integral of all those is this, no matter what, regardless of path taken. So regardless of path taken, the work done by this gravitational force is equivalent to the decrease in potential energy of the system. Now, some of you that have super duper memories remember, hang on, that. We'll get there in a second. Because this result of saying the work is equivalent to the decrease in potential energy is something that's popped up before. Again, if you have a heck of a memory. Now, let's take a little bit of a different view. And that, remember, here we assumed that we were, quote, in this room, quote, near the surface of Earth, where gravitational force has a constant magnitude that we can call mg. But what if we're not in that situation? Sorry, scratch that for a minute. I got a little bit out of order. So let's sort of baseline here and say that we've seen this result before. We'll get to that in a minute. But when we go from one place to another, when a system changes configuration, a two-mass system with gravitational potential energy, when a system changes configuration, it doesn't matter how that configuration changed. If the configuration changes, you know, by the same amount, it doesn't matter how you do it. This is a fundamental truth. Okay? Now here's another fundamental truth. Guess what? If we say, I don't care how we got from here to here, if we then go back from there to here, if we take a closed loop, well, guess how much work would be done on the way back? Well, the same as this, but negative that, right? The system would, you know, the system has a change in potential energy going from start to end, and an equal and opposite change in potential energy going from end to start. So regardless of path, the work is zero. The net work, and that means around a closed loop, closed path. Regardless of path, we end up with no net work being done. That's another definitional thing. We've come up now with some definitional things about what it means for a force to be conservative. All right. One is that around a closed path, work done by a conservative force is zero. Number two is that work done by a conservative force is independent of path. And that's here, right? We said it doesn't matter which path is which. This is how we're doing the amount of work done along that path, and we get the same answer no matter what. It doesn't matter which one of these paths we took. All right, and the third one, well, we'll get to when I remind you of this. So here's what we're talking about with our good memories. We talked the other day about how much work a spring force does as an object, as it moves an object from here to here. Right? Here's a graph of the spring force function, and we can find the work by integrating that curve, which doesn't happen to be curvy, but that's okay. We don't need to really integrate because we can just use geometry, right? And there's the amount of work for part of it, and here's the amount of work for the other part. And we add those two amounts of work up, and we get this. And most of us recognize that that's that. And oh wait, the work done by this spring force is equivalent to the decrease in potential energy of the mass spring system. And as a lot of you guys know, or maybe all of you know, there are a couple of conservative forces in the universe. There are several of them. But the two main ones that we've spent time talking about in introductory physics are gravitational force and spring force. Those are conservative forces. And look at the properties that they share, or a phenomenon that is common between them, and that is, look, the work done by the spring force is equivalent to decrease in potential energy. The work done by a gravitational force is equivalent to a decrease in potential energy. So that is a by definition statement about conservative forces, right? Work done by a conservative force is equivalent to the decrease in potential energy of the system upon which that force acts. Okay? Okay, now, let's apply that to, let's do a, we don't have to, I suppose, but let's do a derivation of the potential energy function of a mass spring system. And we're going to use this definition of a conservative force to do that. All right, so if we say, well, here's a spring force function, it looks like this. F is negative kx vector vector, right? That's Hooke's law. This force looks like that. All right, if we wanted to derive potential energy in the spring's mass system as a function of x, well, here's what we do. We can say, well, that the work done by that spring is negative delta U. Or we can say that there's a little bit of work done that accomplishes a little bit of change of potential energy. Well, there's a little bit of work done. That's this. And in this case, it's going to be our spring force. So if we want to find U as a function of x, well, here's what we can do. We can say that, I'll just rearrange, du is negative f spring dot dl, and thus if we want U, we add up all the little du's, and we add up all the little f dot dl's, and therefore U as a function of x is going to be, let me take out this first negative, and then we'll integrate. Well, what's the spring force? It's negative kx, let's call it in the I hat direction. Right? Let's say that this is a mass spring system that's on a horizontal surface. Right? Here's a springy do, and there's our object. So, well, dot dl. And what's I hat dot dl? Well, guess what? Guess what dl is? dl is going to be a distance along that axis. So it's really, so dl is really a dx. All right, and so that means that I hat dot dl is really I hat dot dx vector, which is really dx. That's a strange thing. It seems, I mean, you can gloss over it to some degree, but right, I hat's a unit vector that means one that way. And dx is dl, which means a little tiny vector that way. So what we have is a little tiny, we have one, so here again, we have one dot tiny. So we're saying what's the component of one, what's the magnitude of that times the magnitude of that times the cosine of the angle between them? Well, it's that. It's a tiny little dx scalar. Right? Result of a dot product or a scalar product is a scalar. So this really simplifies to U of x is, well, let's do that. And we're really doing kx dx. And I'm going to do an indefinite integral here because we want not a delta u, we want u as a function of x. So this says that, well, u as a function of x is 1/2 kx squared when we integrate kx dx, plus c, right? We need our constant of integration. But we know that, Well, when x is 0, when this x is 0, when a spring's displacement is 0, there is no potential energy of a mass spring system. So that C is 0, and there you go, right? I mean, why did we do that? Don't we know that already? Sure we do, but what I'm trying to help you apply or help you see is that any and every potential energy function associated with a conservative force can be derived by integrating, well, by using a definition of conservative force. All right, a definition of conservative force is that the work that it does is equivalent to the decrease in potential energy, and so we can use that relationship between really work and potential energy, but in this case force and potential energy, to relate the two. So if we know a statement of what a force is, we can derive a statement of what the potential energy function associated with that force is. And what does this thing look like? Well, I mean, this looks like this. It looks like a parabola. And why does it look like a parabola? Well, check this out. If we say, well, let's go from here. This says that du, maybe how about this? It says, look, we can say that F is negative du dl. I'm going to say dx because there's only motion along our x-axis. So it says that the force function is the negative derivative. Do you get what all I did was algebraically rearrange here? It says that the force function is the negative derivative of the potential energy function. All right, well, check it out. Derivative means slope of, right? Well, look, here's a slope of 0. All right, yeah, we get a force of 0. Look, we get a smallish positive slope right here. Well, guess what? We get a smallish negative force there, right? We're saying here's slope, here's negative of slope. That's what force is. So here we get, look, later at this position, we get a bigger positive slope. Well, that corresponds to a bigger negative force. And the same thing happens over here. I'll just do one of them. Here's a medium size negative slope. Well, that means a medium size positive force. Now again, we know this Hooke's law and this potential energy function for a spring to be what they are, but it's nice to see that that agrees with a fundamental relationship that we've now developed. All right, let's look at a different one. This one's a little bit harder. Here's a two-mass system. Again, it's a gravitational potential energy thing, but now we are not limiting ourselves to saying that we're near Earth's surface. Now we can be anywhere. All right, and not only that, like we said, we can take an object on any old path we want from A to B. It doesn't matter. We've defined that it doesn't matter how we get from one place to another. Potential energy is going to change by the same amount. And we want to derive the potential energy function UG as a function of, well, R. R meaning the radial direction away from the center of, here's Earth, let's call it, or planet. So how do we do that? Well, we're going to use our definitional statement that says there's work done by the conservative force that's equal to the decrease in system potential energy. That means that there's a little bit of work done. I mean, quite literally, guys, like, I have this memorized, but I kind of, every time I do this one especially, or maybe any of these, I kind of am like, wait, which one is the derivative of what? So I start with that statement. And then I can get here. Well, D, a little bit of amount of work is a little change in potential energy. Okay. And then a little work is F dot dl, and that's a little change. So I don't have to have this memorized. What I can do is start with the fundamental statement and get where I need to go. Okay, and then if I want to find the potential energy function, I can integrate both sides. Watch this. I'm going to move that negative over here. Okay? And then that says, okay, right. So u is going to be the negative integral of f dot dl. Okay, so the object, let's say, is here. The force on the object is this, Fg. Well, what is that force? That force is, first this negative, that force is of magnitude g m1 m2 over r squared. It points, well, this way is the positive radial r hat direction. So gravitational force points in the negative r hat direction. Dot dl vector. R hat dot dl vector. R hat dot dl vector. That looks, all right, so here's a dl. Little tiny dl. R hat is this way. So so this is 1 that way. This is little tiny. So it's 1 times little tiny times that angle, that cosine of that angle. Or it's literally saying like it's really like r, the magnitude of r hat that's times the magnitude of dl parallel. Well, dl parallel, all right, let me zoom in a little bit. We got the r hat, we got the arbitrary dl. Well, here's like dl parallel. And dl parallel is tiny little dr. That's it. R hat dot dl vector is dr. We're saying magnitude of 1 times magnitude of tiny. Well, that's tiny. And we're not saying in the direction. We can't say that because scalar product is a scalar, not a vector. So the answer is, it's a little tiny dr. So this thing turns into u is, watch, we get 2 negatives. Bang, bang. We have g, yeah, sure, fine. G m1 m2 over r squared dr. This is really, excuse me, this is really, I can do this, g m1 m2 integral r to the negative 2 dr. U of r is g m1 m2. Now, what I haven't done, I'll just leave it the indefinite integral. So let's see, integral r to the negative 2 dr is negative r to the negative 1. Right? Remember, if you were to differentiate this dr, you do negative 1 times that and decrease this by 1 to get to negative 2. Yep, that's the correct integral. Right? And so we get that u as a function of r is negative gm1 m2 over, whoops, not over 2, over r plus c. And now with these, there's really no such thing as a definite amount of potential energy. That's not really important. What is important is differences in potential energy. What we have to do here is say, let's agree on something. Let's agree on the fact that when r, the separation between two objects, that's what r means, when the separation between these two objects is super big, that the system has 0 potential energy. Right? So when r is approaching infinity, then u of r is 0. That means this can just go away. Is that true? Yeah, r is infinity, then 0. Well, that's the way it works. Hang on. Yeah, that's just it, right? If r is huge, u of r is assumed to be, or everyone agrees that there is no system potential energy, so that C value is not there. And so this is the definition of the gravitational potential energy function of a two-mass system. It's a strange function, negative GMM over R. All right, so let's look at what that means. All right, first of all, f as a function of r is an inverse square thing. We could be careful, but I'm just going to sketch. It looks like that. All right, this is f is negative gmm over r squared r hat. Right, u of g, u of r, excuse me. And this should be of r too, is negative GMM over R. No vector, no R hat, none of that. And this does a little less drastic. So first of all, what does it mean for this? This is pretty neat. This says that potential energy functions, well, as R gets bigger, U gets bigger, right? And the magnitude isn't getting bigger, but the number is getting more positive. And that means more. A more positive number is bigger than a less positive number. There's more of it. So first of all, we have a function that gets bigger as r gets bigger. Well, that's good, right? If you take a book and move from here to here, r gets bigger, and we would say that u gets bigger. Now, we would say that u gets bigger by mg delta y, but that's because we're saying g is constant, and this doesn't. This has that built into there. This has gravitational field strength built into it. So these two things agree. There's no negative in here, but again, what doesn't matter is the number. What matters is the difference. And we do say that UG gets bigger when we lift something up, and that means, well, the same thing that this graph says, at least qualitatively, that when we lift something up, slash R gets bigger, there's more UG. Right? We get a positive delta U. It also says that the biggest U can get is 0. And that works really nicely because what we need a function for which the farther away things get, the farther we go along our axis, we need more potential energy, but the most potential energy a system can have is 0. We need something that increases to a maximum of 0, because when things are infinitely far apart, then they have no potential energy because the field made by one is infinitely weak when things are infinitely far apart, and therefore that field can't do any work. So that's why this function is pretty neat and agrees with, well, fundamentally how the universe has to work on a gravitational basis. Okay, we can also do what we need to do, right? We can, and by that I mean this. We said, well, let's see, F is defined to be negative du dl. I'll say dr. Right? That's the rearrangement of this to write it in terms of F. And now what we can do is say, all right, well, this means slope of u function and negative of that. So let's look what we get. We get big positive slope, and we get big negative f. We get smaller positive slope. We get smaller negative f. Okay, so those two functions qualitatively do agree with the way they have to. So what you'll do in some cases is, you know, some crazy question will say, hey, guess what? Here's the u function. It looks qualitatively like that. Ooh. and you'll say, huh, what does an f function have to look like? And you'll quite literally say, well, let's see, the function has a positive slope, that's a negative f, and then a zero slope, that's a zero f, and then a slope that's negative and getting more negative, well, that means a force that's getting more and more positive, and so you can do these sort of translation operations from one function to another via this idea. And this is the way it's easier to do as opposed to trying to do it this way. It's hard to say the area, it's harder for me to say, well, the area's got to be doing this if the u is that. That's harder for me to do. All right, so I like to, and there's a whole nother video on this, but maybe I'm looking too far ahead. Okay, so maybe for sure U spring 1/2 kx squared you've heard of, introductory physics folks. Maybe introductory physics folks, you've seen that gravitational potential energy of a two-mass system is that, but now we know why, or now we can justify how we get there. And we get there via this definitional statement about what it means for a force to be conservative. And we build that all the way into this good integral. All right, we have to do this crazy sort of thing. Oh boy, I mean that took me some real banging my head against the wall to get. Maybe less so for you, maybe more so for you. For now, what you'll have to do perhaps is say that just turns into dr. But it's nice to say, just trust me. We can justify, right? We can justify that. Yeah, okay, I see that that's dr. All right. In the same way that we can say, yeah, okay, I'm all right with the fact that, I hat dot dl is the same as dx. Okay. All right, so let's baseline a little bit and just say for any conservative force, we have our definitional statements, right? That work is path independent. Work around a closed loop is 0. So let's just put those in there. 1. Work is independent of path. 2. Work around a closed path is 0. 3. Work done equals decrease in system potential energy. And well, that means that we can write a couple of fundamental statements. We can write that, like, for example, let's see. I can't remember how to do it, so I'm going to say this. Okay, dw is negative du. Okay, here we go. I'm going to say du is negative f dot dl. Okay, good. That's good. And we can also say that f is negative du dl. All right, so these two relationshipy things are the ones that you'll use when you want to know, well, like in this case, well, this really we're going to do like this. We're going to say that u is negative f dot dl. And then you'll use this sometimes as sort of the opposite of that to relate. Well, like if you know the force and you want the u, here's how you do it. If you want the wait a minute. Yeah, if you want the u and you have the force, this is what you do. If you want the force and you have the u, this is what you do. Don't you hate when I put all these arrows everywhere? All right. Okay, so that's definitional stuff about conservative forces. Okay? There are some, arbitrary sorts of questions like these, right? Hey, here's some potential energy function. It looks like that. Okay, fine. What's the force function, right? So all you do is you do this stuff. Okay. Then there are questions like, equilibrium. Where's an equilibrium? What does equilibrium mean? Oh yeah, equilibrium means force is 0. Oh, that means that the the derivative of this potential energy function must be 0. All right, so there's ways you can interpret these questions, and then we'll get into, what do these functions look like, and what does that mean, and this idea of where are things in equilibrium, and what does that mean about their equilibrium? Are they stable or unstable? So that's the next stuff coming. Okay. All right, folks. Farewell. Thanks for boy, 40 minutes. Told you, deep dive. See ya.